Well, just like Royce mentioned, my name is Eric Poitras, so I'm only recently started my appointment at the University of Utah about 2 years ago, teaching full-time in the Instructional Design and Educational Technology program over there. And the title of my talk will be Modeling Learning Performance with Adaptive Technology-Rich Learning Environments. So Royce mentioned that you have a very diverse student body, so some coming from industry, some coming from the more academic stance. So I thought I'd start off with a basic definition of what is adaptive technologies. Well, if you Google adaptive learning, you'll find it refers to an educational method which uses computers as interactive teaching devices to orchestrate the allocation of human mediated resources according to the needs of each learners. And really, the last part of that sentence is really critical to understanding what are adaptive technologies. So trying to improve their capabilities to personalize or individualize instruction to make sure that the content that's delivered to learners is the most well-suited considering their specific needs. Now, in considering some of the important milestones of the development of web-based technologies and looking now at what they're capable to do in terms of personalizing instruction, we've been very fortunate to live through some very important developments throughout our lifetimes. Consider that only 26 years ago, we saw the advent of the World Wide Web, followed by 8 years ago, and only in 1998 with the Google search engine. Looking now at today, Google indexes on average over 47 to 50 billion web pages on a monthly basis. So for me, I think that's really interesting. I'm kind of interested in terms of how can adaptive technologies leverage some of these existing online resources. Not necessarily building new tools, but how can we make better use of some of these existing resources that are available online to improve instruction. Another shift that we saw focused, especially in the last decade, is the transition between Web 1.0 tools to Web 2.0 tools, which really was made possible through the advent of more sophisticated JavaScript libraries, better processing on the PCs, and also with larger storage sizes for the web servers, which allows users to not simply be consumers of information, but to allow them to create their own information as well as to share it with others. So some of these functionalities are available through tools which you're all familiar with, I'm sure, such as discussion groups, website hosting services, wikis, blogs, and media file sharing services. So in considering the role of technology in personalizing instruction, I think it's really interesting to think about ways in which some of these tools can foster these types of better collaboration, and also the creation of instructional content. Now, looking now at the scientific literature, you'll find in some of the major reviews of the literature that was done on intelligent tutoring systems and some of these adaptive instructional technologies will give a broad definition of what they're all about. But what's most interesting is to look at some of the commonalities across some of these different systems. We find that they tend to rely on common representations to undergo in specific processes that allows them to interact with the users in different ways. And that really goes at the heart of what personalization is all about. So for instance, they'll rely on representations such as a domain model, which states a certain set of learning objectives, some common misconceptions that learners might engage in, or some errors that might have while trying to solve problems, or a set of ideal answers. Now, adaptive technologies rely on a learner model to continually update relevant learner states against these domain models. So for instance, it'll try to infer whether or not a student at a specific point in time is exhibiting that particular misconception. So in order for the system to rely then on the instructional model to deliver some content that will help the students gain a better understanding of that topic. So here are some of the underlying processes that are occurring in these systems. Refers to the ability to capture user interactions in real time, so to analyze it, to make some of these inferences, and then to select and then decide how to deliver the most suitable instructional content. Again, through interactions here that occurs either at the macro level or the micro level, so referring to the timing. So at the macro level, either before or after the task is performed, such as when you reorder tasks to optimize the sequence so that it challenges the learner to the right levels of their abilities. And also at the micro level, so during task performance through delivery of things like hints, feedbacks, and prompts. And the article, if you're interested in some of this literature, the article written by Kurt Van Lane in 2006 is very telling. So to go over a few examples of adaptive instructional technologies, this system I worked on during my doctoral thesis over at McGill University, so under the supervision of Dr. Susan Najwa. was referred to as the meta-history reasoning tool. So it was an intelligent tutoring system that was designed to support students to reason about the causes of historical events. And so just to give you an example of some of these underlying processes, so the students began with the training module that's shown here on the upper right corner, where they were shown examples of some of these historical thinking skills, which through a categorization task, the system was able to infer the rate at which they acquired those skills. So after they've actually mastered the skills up to a certain level, so they would then transition to the inquiry module where they would be expected to use them with the benefit of this virtual pedagogical agent that kind of interacts with them and that helps them to set a diverse set of goals for their inquiries. In this case, they were investigating the causes of the Acadian deportation, which happened in 1750. And so the system was designed to make sure that they set a range of different diverse goals for building arguments and formulating their own explanation for why that event actually occurred. Another system that I worked on during my postdoctoral studies, again in the same lab, was called BioWorld. So BioWorld was designed to support novice physicians to diagnose medical diseases. So a learning session began with this patient description where the patient complained about certain symptoms that they were having, and the system relies on this novice expert overlay model to look at the evidence items that novices rely on in order to justify their hypothesis, and then compare that against how an expert would go about solving the same task. Now the reason for doing so is that you can highlight similarities and differences. Highlight similarities in terms of the highlighted symptoms from the case description that were identified by the expert but maybe missed by the novices, such as profuse sweating or dizziness, as well as some of the lab tests that they could order, such as the urinary metabolites results. And now this information allows the system to then individualize how the feedback is delivered to the user by using this interface shown here. So you can see that there's like little exclamation points with regards to the evidence items that novices missed, and that's combined with a more detailed explanation of how an expert actually went to go about solving that case. So this figure here shows an overview of my presentation. So I mostly wanted to talk about some of our current works that we're doing in the lab in relation to 3 types of adaptive instructional technologies, including content management systems, web-based augmented reality, 3D and game environments, and open-ended learning environments. And I'll talk about some of the methods that we've used and some of the recent findings that we've obtained, and then briefly mention some future directions. And if you don't mind, I'll just sit. I haven't gotten quite used to the dry weather over here. So I tend to do this on a regular basis when I teach. Now, the first project, which referred to content management systems, referred to our collaboration with MedU. MedU is a worldwide consortium of medical educators that develop virtual patient cases, teaching resources, and assessment tools. And the platform is available online, so medical schools can register for their students to practice diagnostic reasoning skills and then receive feedback. Now, the aim in this project was to personalize how we deliver feedback on the basis of the learner annotations that are written using a tool that's available through their interface. And as a proof of concept, we began by analyzing the case of Mr. Monson, which presented with acute myocardial infarction, which is a really fancy way of saying that he had a heart attack. Now here you can see the main user interface of that system. So on the left-hand side, so you have access to the navigation sidebar so that the students can revisit at certain points, different points in the case. Now the case description evolves constantly. So all throughout these cards, based on the learner's decisions, you'll have the patient's symptoms that evolve through time, either gets better or actually deteriorates in their vital signs, depending on the decisions that the students actually make. And they're allowed to make these decisions mostly through multiple choice questions that are presented here at the bottom of the interface. These questions also serve for the purposes of assessment, so that we can gain some information on some of the decisions that the student make with regards to the diagnosis, how they treat the patient, and also how they manage some of these vital signs and some of these changes in the patient's symptoms. Now on the right-hand side of that interface, there's available the annotation tool, and the learners can write in these annotations, mostly referring to patient symptoms that they were thought were relevant, or a lab test result that pertain to their diagnosis, and also a list of potential diagnoses to consider as part of their differential. And at any point in time, so the learners can add some of these annotations, reorder them, or delete them while they're working on the case. So we were interested in extracting some of the linguistic features that characterize those annotations to see whether or not we could predict, especially incorrect answers made to some of these multiple choice questions. So in total, for the Mercer-Monson case, we were working with 4 to 5 multiple choice questions that were delivered to learners for 8 cards, so 8 different pages throughout the case. And again, so these assessments serve to provide feedback to the learners, so formative feedback while they solve the case. So you can see here for all their decisions, they're all automatically prompted with these little check marks indicating whether or not a specific choice was correct or not. You also have access to the total distribution of choices that were made by previous users of the system, so that they can get a gauge of how difficult the item actually was for them to answer. And after they've submitted their answers, so they have access to the expert's explanation of why that particular decision was the best at that given point. So looking now at our data set, so we had to work with a range of about 12,947 to 13,262 attempts that were made by learners to answer each of these items. And we coded these items as to whether or not they were correct or incorrect. Now, on average, the case difficulty was moderate. So that type of diagnosis is very common. So we found that acute MI was listed in the differential diagnosis in about 67% of all cases. So for our data mining analysis, we relied on the 2-step supervised subgroup discovery algorithm to generate some rules, which we would use to predict some of these incorrect decisions that were made by the learners on the basis of the linguistic features that were extracted from these learner annotations. So the rules were generated to optimize the precision of the predictions. So they kind of adopted the following format. So if an item answer is found to be incorrect, well, the term X is mentioned in the annotation. So in the first step of the analysis, we used only single terms, and then in the second step, we added multiple terms to see if we could generate some better predictions. And referring to precision, so here then we're optimizing for the number of true positives relative to both the true positives and the false positives. So we're interested in determining when that term is mentioned, if the answer is incorrect, being the true positive rate, divided by both cases where, yes, the term was written in the annotations, but we had a certain number of incorrect and correct answers that were submitted. Now this figure here shows the total results for our analyses, where we have all of the items that are listed, the 45 multiple choice items here on the x-axis. And on the y-axis, you can see the precision proportion. Now, the bars here that are of different colors indicate the first and the second step of our analysis. And we found some slight benefits in terms of adding the second step where we use multiple combinations of terms. You'll also notice that the level of precision coincides quite well with the item difficulty, which is indicated by this little bar here, saying that basically the proportion of incorrect answers that they obtain tends to correlate very well with the rules that are generated and how well they perform, which is really what we want, because we're interested in detecting some of these misconceptions, which are indicated by errors in their answers to these items. So in the following 2 slides, I'll refer to item number, for card number 3, item number 4, which obtained the highest level of precision on that first step, just as an example to show you the output that's generated by the analysis. So in the first step, again, we were working with single terms. So these terms are used as antecedents to the rules. And so they follow the following conditions. So if the term segment, for instance, is mentioned in the learner annotations throughout the entire session, so we see the following distributions for the rules that were generated, so including the true positive rates, false positive rates, the amount of coverage in our data set, the weighted relative accuracy, and the precision value. So just to give you an example, so whenever a segment was found to be mentioned in the learner annotations, we found in 108 instances where the learners obtained the incorrect answer for that particular item, but only 26 instances where they had the correct answer. So this corresponded to a precision value of 31%. It only accounted for less than 1% of all the cases in our database. Again, misconceptions being fairly rare for this type of case, which is on the more easier end. And we only obtain very relative improvements in terms of weighted relative accuracy, which takes into account both the rate of true positives, false positives, but also the true negatives and the false negatives. So when the term isn't actually mentioned in the annotations.
Did you do any cross-validation with that analysis?
In this analysis,
I'm just curious.
as a follow-up, because we've been working on different iterations of this analysis, but we haven't yet cross-validated, like actually use it as like a classification model and then gather another sample of learners to see how well it would perform in terms of detections. We haven't performed this yet because we would have to wait a little bit more, maybe a few months, so that there's no learners that get scattered in the data.
I was just wondering if those words were actually indicative of people that were actually missing the question, or if it was just by chance because there are thousands of words that they use and these ones were just the ones that happened to show up.
It's a fair question. It's an important question. But at this point, we're not really able to answer it.
Okay.
But definitely moving forward, that would be something to take a look at to
Yeah.
see how well our model actually performs with, especially an external sample that we haven't analyzed yet. But in terms of generating like some more of these insights and gaining better understandings on misconceptions, it's also very interesting to go back and take a look at the actual content. So to analyze some of the HTML information to see where the terms are actually mentioned. So the term segment, for example, appears quite often on the second card, which coincidentally is shown right before they actually answer that item. So using this type of information combined with some of the actual annotations and providing that information to the system designers and some of the medical experts can make it a little bit easier to kind of customize what type of feedback is actually delivered to the system. Because for all they know, the errors tend to be very common, and yet the feedback just isn't written to kind of go about addressing some of these misunderstandings that the students might have about these cases. Now, we'll transition here. So the second project that I want to talk about is our work with mobile augmented reality applications. So we're currently examining these types of applications as they're very commonly used in historical heritage sites and museum exhibits and some of these guided tours that are conducted in these settings. And we're interested in examining the conversations that occur between tour guides and visitors, which we believe are very critical to some of the learning engagement outcomes. Now, our aim here in this project was to model the dialogue that occurs between the virtual tour, between the actual guides and then the visitors in order to identify some of the best discourse practices which we could design a virtual tour guide to emulate in the context of virtual tour and maybe even actual ones. And also to improve the design of the apps and the nature of the tour locations that are visited by the learners. So this work is supported by learner environments across disciplines research partnership. So we're collaborating with Dr. Kevin Key, who's at Brock University. He just moved actually to the University of Ottawa over in Canada, as well as Dr. Susan Lajoie from McGill University. So we have a few tours that are kind of ongoing in different sites. This one in particular was my responsibility, so we had to design what we call the Discover the U app, which gives guided walking tours across the University of Utah campus so that we can go about evaluating some of the user experience. So this app is compliant, is available on iOS, Android, and Google Glass devices, since we started developing it before Google actually axed that program. And it's currently limited to 4 locations surrounding the College of Education, so the users learn about the life of Dr. Milton Binion, who was dean for the college for about 20 years and also vice president of the university for, I think, maybe 2 years. So a very important contributor to campus. So the app provides users with multimedia content, so including audio narration. We also have some primary source documents so that users can learn a little bit more about the life of Dr. Milton Binion, as well as some of his beliefs regarding the role of morality in education. And they also have access to some pictorial documents and some old visual photographs and paintings that surround either his life or the actual building from the College of Education. So in our data set here, so we recruited 60 undergraduate students from the educational psychology student pool, and they performed a simulated tour in the laboratory while discussing with a researcher that acted as the tour guide. So we'll use often that strategy, so a combination of simulated tours and then actual tours in the actual setting. We utilized a total of 12 self-report items to assess activity-related emotions, including enjoyment, boredom, and frustration and anger, as well as 16 sentence verification task items and inference verification task items to assess their understanding of the topics that were mentioned within the app. Now here for our analysis, we relied on the classification by clustering approach to detect profiles of engaged learners on the basis of the discourse rules that were utilized by the tour guide. So the decision tree algorithm that we used generated some rules which allowed us to identify some of the best discourse processes, so the conversation threads that would lead to better promote learning engagement. Hopefully so that we can use that information to make some decisions with regards to our design for the virtual tour guide, or to redesign some of the audio narration, or to create some additional learning paths for students to pursue during their visit. Now you can see here a screenshot of the interface that we had for the simulated tour. So we relied on these 360 panoramic photographs that were animated, so the users could actually go and walk through that space, so they can either move forward to get a better view of an object, or move the viewport from side to side to get a better view of some of the larger locations. Now the documents that were available on the app were also shown at the bottom of the screen here, so that the students could access whichever modality that they preferred for reading the content. And there were also some navigational buttons that allowed the users to visit each tour location that were located on the left and the right-hand side. Now here you can see our experimental setup. So we relied on a range of different sensors to gather data from the users to better capture their experience, because we're very interested in modeling these learning engagement processes. So we had a depth sensor that captures their posture and their movements while they're going through a simulated tour. We relied on the webcam to capture their facial expressions. We had physiological sensors, including a heart rate sensor and a galvanic skin response sensor to measure changes in their arousal level as they were going through the tour. This mic here captures all the speech that occurs between the visitor and the tour guide, so that we can transcribe it and code it for later analysis. And over here, so with me serving as the tour guide sitting over here, so I was able to log behavioral observations using an observer software that we developed in the lab, which in this case, logging was very simple, so we were just taking note of whenever they arrived at a specific tour location. And that information was analyzed by the app in order to deliver a prompt that the tour guide could rely on in order to inform the discussion. Now this heat map here on the right shows each of the prompts that are represented as columns. And whenever an area was shaded, so the prompt was actually delivered by the tour guide, and all of the areas that were not shaded, so the prompt was not delivered by the tour guide. So every conversations that occurred between the tour guide and the visitor were always slightly different for each and every session. So that after the fact, we can go about analyzing what type of prompt is actually most effective. So we relied on a k-means clustering algorithm to try to find different groups of learners in terms of how they were distributed in their scores for both the activity-related emotions and learning outcome scores. We obtained in this case by optimizing, well, minimizing for the Davies Bouldin index, as well as the sums of squares between the centroids that were used by the as well as the data points, three different groups that were mostly distinguished by the levels of activity-related emotions. So you'll notice that there's a high engagement group here, a medium engagement group there, and then a low engagement group here that tends to be a little bit lower on enjoyment and then a little bit higher on boredom and frustration. Now these groups were not fairly well distributed, were not fairly well distinguished in terms of learning outcome scores. So you can see they obtained pretty much slightly similar learning outcomes there. They're fairly on the higher end of the scale, perhaps with the exception of the SVT scores, which are on average 10 out of 16. And in terms of the distribution of learners in terms of all of these groups, so we found that only a minority of them, like about 11 out of all of the 60 students, fell in the low engagement group, with more of the students falling under the medium to high engagement groups. So what's most interesting about this analysis is looking at how we can go about using the conversational prompts to classify whether or not the learners fall under each of these groups. So each of these nodes here corresponds to different conversational prompts that were used throughout the session. And with regards to these little decision rules here, so if, for example, prompt number 22 was mentioned, which is indicated by a value greater than 0.5, so I should probably have labeled that qualitatively so it makes a little bit more sense. But whenever a prompt was mentioned, so it was obtained a value of greater than 0.5 here for the rule. If it was not mentioned, then it was lesser than 0.5. At the very end of this decision tree here, so we're trying to classify our students in terms of these three groups. And so this type of analysis allows us to basically identify conversation threads where the learners are most likely to fall either under a low to medium engagement groups, a low to high, both the low engagement groups and then the highly engaged groups, which are threads here that are really interesting. So that would be indicative of, we would have to go back to some of that process data to look at individual differences to kind of explain why both of these groups are kind of falling together under the same conversation threads there. And then finally to the medium and high engagement groups, which are probably the conversation threads that we want to most promote, to take a look at the topics that were discussed to see what really got people interested during the tour. And I should mention also that this decision tree was generated while optimizing for a number of parameters for how the tree is built, including the minimal gain value, the leaf size, the split size, and the confidence levels. So we generated about like more than 1,000 iterations of this decision tree, and the highest level of accuracy that we obtained for classifications was at about 72%, corresponding to a kappa value of 0.56.
So Eric,
Yes.
can I just, so what would you do with this data or this analysis? Are you using it as a way to change how you would teach the tour guides? Like what kind of prompts to use, or what do you do with the data once you've got it?
Well, it does have very important implications for training. Yes. If we find some threads of conversation that seem to just not work, I mean, we would probably tell the tour guides, hey, maybe you should focus less on these topics. Try to talk more about these ones, because we see that if we actually had some good scores for learning outcomes and good gains, then we can make and show them that, to see, well, these types of conversations actually lead to better understanding of the topics, people seem to be more engaged. So that's probably the focus that you want to mostly attend to. Since in this study we were doing it in a simulated context, so everything was available online, we're kind of interested to see if we can design a virtual tour guide so that, for instance, I wouldn't have to give the tours all the time. The students could just simply interact with the pedagogical agents that would be presented on the side, and then hopefully that agent would emulate some of these best discourse practices, and we would see the same learning outcome scores in terms of the increases. That's a little bit more like future work, really down the line. And there are some complications, like some of these conversation threads we'll notice that are very take this one for instance, like prompt number 22 was mentioned. However, if prompt number 14, 17, and 23 were not mentioned, this presumably leads to better outcomes. But really what's that saying is that, well, you should use prompt number 22. Well, is that really a conversation? I mean, it's not really elaborate. I mean, in this case, it's not really telling in terms of designing how the agent should interact. But maybe it's a little bit more useful in terms of changing maybe slightly like the focus of the app itself. Like if all of these conversational nodes, and I don't really know this because I've done this analysis only a few days ago, but if all of the nodes actually focus on the same type of topic, maybe like the third location, for instance, then we might want to focus on just starting a tour from that location, not really changing how the agent converses with the visitors, but instead changing the whole nature of the tour, just changing the audio narration and getting more in-depth into that particular topic, which seems to relate more to that student population.
I have one other follow-up question. Just wondering, one of the assumptions behind this seems to be that all of the tourists or the participants are coming from the same place, right? Whereas you might have, I mean, if you cluster it based on certain characteristics of the participants too, you might find that for certain participants, a certain disposition or certain pre-knowledge or whatever, their path actually looks quite different than somebody who has no prior knowledge of the site or the...
Yeah, maybe somebody with a certain goal orientation would
Yeah.
score higher in the learning outcome scales, and then that would actually differentiate itself as a separate subgroup. I mean, that begs the question of why aren't we using more of these questionnaires to get some better representation of some of these learning outcomes. But definitely, there's some there's some ways that we could kind of expand that analysis. I mean, what I think is the really strong aspect of this is using both the simulations in the laboratory and the actual field studies. We found, like in our studies at McGill, that there are some slight differences. Not surprisingly, people tend to be a little bit more bored in the lab than actually going through the tour, so you have to take that into account. But most of the literature is very limited by the fact that these tours are very hard to develop. I mean, it's just hard to travel over there, get like, you know, huge samples to undergo some of these tours, and some of these cultural heritage sites, they're far away, so, you know, they're not really accessible. That really limits the field, so I think the simulation method is like a nice complement. Maybe not the entire truth of it, but at least it's something that we can get like bigger sample sizes that we can start creating like some general conclusions about their experiences.
So is it like, so it sounds like the main purpose of the app is so they have it on their smartphone and they're actually going through the campus. But then, like, you don't have actual, like, there aren't as good of tools to like evaluate what they're actually doing. So then you're just doing like a simulation where they're, instead of being on their phone, they're on a computer and they have everything tracked.
Yeah, the apps are available on the content management system, so they're published through Gittygo and Izzy.travel, which is nice because it allows us to intersect with the Google Glass. That was really the original intent of the tour, having people just walk around with these glass devices so that we could see how they kind of felt about it. But that constrains a lot of the options in terms of the user interface and what we can log. For instance, we can't log much of anything through the content management system. There's no database on the back end where you can gather that kind of information. Furthermore, with the Google Glass device, it's just a terrible display. It's like this small little screen on the upper right corner of your eye, and you can barely read anything. I mean, presenting like a document through that modality is just terrible. It's just easier to do it with a handheld phone. So a lot of the constraints of the interface kind of plays into it. We were interested in developing like a web-based version of that app, actually being able to collect some of these user interactions in real time and then hopefully analyze it. But we're still kind of debating whether or not that's the right decision to kind of move forward with the right direction.
I have a question. Can we go back to the previous slide? Yeah. Why don't you think engagement had an impact on student achievement?
Well,
I mean, was the assessment easy enough that even the board unengaged students could do well on it? Or
I'd say that the assessment was most easy in terms of the inferences of the IP&T scores, because we obtained lesser variability on that, and then the scores were pretty high. The SVT was a little bit more spread out, and we're still in the middle range of the scores, so hopefully we've been able to detect something through the SVT if there haven't been like any learning outcomes.
right?
Whether or not, I think, for the activity-related emotions, it's hard to say. I mean, my gauge of their subjective experience, and that's just my personal view, is that it's a little bit easier to respond to those items, to answer them like using like the highest score or like the lowest score. Like they'll kind of dramatize the experience. They say, oh yeah, this was completely boring. I hated this. Like 1. Or like saying, oh yeah, I love the idea or something. Or maybe they just wanted to please me and then just rate it 5. So, and keep in mind that for the SVT and the IVT scores, those are true and false items too. So that adds to it. For the activity-related emotions, those were Likert scale items.
Okay.
So it's possible that the nature of the assessment has kind of like some role to play with regards to the spread of those scores.
Yeah.
But again, that's just really postulating at this
Yeah.
point. Maybe just looking at the conversations and seeing how in-depth they thought about the topic while they were conversing would kind of corroborate some of these findings.
Yeah.
We just haven't done it yet.
Yeah.
I just literally made the results about like
Yeah.
5 days ago.
Thank you.
Alright, so let's move forward then to the, how am I doing on time? So I'll move through this last project really quickly. So this is the work that we've been doing with an open-ended learning environment. So we developed the Vesta suite of software applications to support this work, and these were designed to facilitate the development of technological pedagogical content knowledge in pre-service teachers. So pre-service teachers from the College of Education rely on the M-Browser, which is an intelligent web browser that tailors the delivery of both online resources and lesson plan examples that are written by previous learners, and they are delivered based on their specific trajectories across while they navigate the web. So rely on a combination of methods to going about evaluating the design guidelines of the browser, using both simulated learners, web crawls, and controlled experiments. So this is a screenshot of the main user interface for the system. So learners begin by interpreting this case description where Linda, the math teacher, is complaining about an issue in her class, and their goal is to design a lesson plan that addresses that issue. So they can begin by using the lesson plan details panel, which is available here on the right-hand side, to plan certain aspects of their lesson plan. So including setting the objectives, so identifying the student population, the grade level, the Common Core standards that that's aligned with, as well as the overall timing of the activity amongst other of these details that are available. The learners can navigate the web using this web browser window here in the search bar. And while they're navigating the web, so whenever they encounter an online resource, they can go on the slider bar here to rate how relevant that online resource was to their lesson plan that they're designing. Now, they can also request additional online resources that are delivered by the system by clicking on this little button here. So they'll show a little title, caption of the page, and they can click on this little button here to go and present the actual page. Now, in using this interface, they can translate both the content of the online resources and the previous examples that were written by other learners of other lesson plans to edit their own lesson plan here using this text box. Now, in doing so, they can revisit online resources that they've rated in the past, as well as the case description by clicking on some of these menu options here. They can request additional lesson plan examples, which are showcased here at the very bottom. They can coordinate amongst multiple sources of information by splitting the browser view. And they can also request hints by clicking on this tree-like structure to get some ideas in terms of some recommendations for the ideal structure of their lesson plans, as well as a link to all sorts of small examples. Now, most of our work in this area has been on crawling the web and building our database of online resources so that we can generate some of the recommendations through the system, and also studying by simulating probable learner trajectories across the networks of online resources to study how our algorithms perform and that allow the system to make these recommendations. And we're just currently in the process of analyzing some of the data that we've obtained for our first randomized controlled experiment, where we've compared the non-adaptive to an adaptive version of M-Browser in terms of fostering self-aware learning processes and also supporting pre-service teachers to develop technological pedagogical knowledge. Now you can see here, so this figure shows like a visual representation of the network of online resources. So all the little nodes here represent web pages that we've crawled from the web. And again, so we do some text mining analyses to interrelate each of these nodes in terms of these little links that are weighed on the basis of, in this case, the cosine similarity, which is the amount of overlapping words between each of these pages. So this visualization, we applied a force atlas algorithm to it. So the nodes that are more closely located to each other are presumably on similar topics. And what's interesting is also we've manipulated the size of the nodes, so the ones that are more central to the network, where we have more links, are shown to be bigger. Now, what's interesting with this approach, and the aim of our efforts here, is to try and figure out a way of organizing all of the online resources that we obtain from the web. So we rely on some clustering techniques to detect subcommunities, which would warrant the reorganization of the network, which is quite large, into smaller subunits that are on distinct topics. Now, in this case, we applied a Louvain detection algorithm to this, and we found a total of 7 communities. Again, by filtering for the amount of links, so we'll typically filter for different network configurations where we only keep like links of a certain weight, for instance. Now, these weights tend to range from 0 to 1, so 0 meaning that there's no overlapping words, and then 1 meaning that there's total overlap in the words that are mentioned across the page. Now, in this case, we didn't have quite a good fit for the quality of the solution, so meaning that there was no basis for actually subdividing the network into all of these little clusters, into separate networks. And all of the communities that we've identified here in our analysis are indicated by different colors. You have your blues, your purples, and so on and so forth. Now, using these kinds of representations, so these networks of online resources, we can study how different learners might navigate across it and how the system is able to generate recommendations. So we ran simulated learning experiments. So in order to do so, we've created 10 different networks to start off with of different sizes, including all the way from 10 to 100 nodes. And we start off with a few assumptions for our simulated learners. So mostly being that the first page that they'll visit is arbitrarily determined. So the amount of pages total that they also visit is randomly set. So we use random distributions to determine this. And also their ratings for the usefulness of these online resources is also arbitrarily set, with one exception. So there's always one node within the network that's predetermined as being the most useful. So what's interesting is to see how quickly some of the algorithms in the system are able to adapt or adjust the link weights to allow the system to make better recommendations. So we want the system to recommend the most useful online resources more quickly throughout the learning process. So we've designed a spring activation algorithm so that every time that a learner rates an online resources being the most useful, it just updates the link weight so it adds to it. So it's based on the sigmoid activation function. So you can see here that up about the point where we've reached 7 to 10 simulated learners here that have relied on the system, that the average link weight values that span towards the target node that was determined as being the most useful dramatically increases. So basically the network that's rearranged itself after about 10 learners that have used the system in a way that presumably we think will allow it to make better recommendations, because when the system makes those recommendations, it's always looking for the nodes that emanate from the ones that correspond to the current page. It's always looking for the link with the highest value for the weight. Yes?
Seems kind of cool. It's like, so is kind of the goal, it sounds like it's almost making like a mini Google service for a specific community where they're like, they can, go and look and say, oh, my peers all thought that these were the top, most useful sites, and then they can.
Yeah, through time we kind of like crowdsource, like a little bit, how the content is rearranged. Like we let the learners rate for the usefulness of the online resources with the assumption that they're rating them, which isn't always the case. And throughout time, the network will just rearrange itself to try to guide new learners to the most useful online resources. This is what we see appear here. So in the 80% of cases, we found that most useful node that was predetermined is recommended to the learners within 10 sites that they visit, in about 80% of cases. So it's all probabilistic. Like it all depends on the rest of the arrangements and the nodes and how they're weighed. So in some cases, we see that doesn't really happen. So that online resources tends to be recommended later. But mostly in the current version, that algorithm seems to perform fairly well within a certain scope.
So this relies upon them rating it, and I think as you mentioned before, they don't always do that. I wonder about, could the same system or results be done using a binary variable like bookmark? So just looking at whether or not someone bookmarked something, ascribe value to that, and then by looking at patterns of bookmarking, do the same kind of thing.
And that would be a much more reliable metric to rely on to make that kind of inference. Another things that we could consider is whether or not they edit the page once the node that corresponds to the currently viewed page is active. So that if they do edits while looking at that page, well, presumably that page tends to be useful. They seem to be using the content. We haven't gone so far as to actually take a look at the content that's viewed in the HTML page to see if how they refer to that in the lesson plan. But definitely those kinds of things are the direction that we want to move towards. It's more like latent detection of those usefulness ratings as opposed to the overt rating, which some users tend to use, but I think that most of them do. I mean, they just prefer to don't go through the trouble. Just because they don't see the benefit. They don't see that they're generating better recommendations through time by relying on that feature. You have another question?
Yeah, I was just curious. So is the pre-service teacher in that scenario the ultimate end user, So are they getting recommendations for these are things that are helpful for a teacher who's preparing a lesson plan? Or is it
Well-
like, these are things that are helpful for your students?
That was the intent of the system. I mean, we mostly designed it for pre-service teachers to go through the college so that they can design whatever lesson plan that they're interested in and also get training in terms of designing better lesson plans. The rationale for that is that we purposely sample the types of online resources that will crawl from the web. Now, in this study, we mostly focus on educational blogs, for instance, that were written by teachers, specifically on the integration of technologies in the classroom. So that instead of doing like a service like Google, which we can do better than Google, we just design a system that's more specific, where it's a very well-defined user base, and only with a database of online resources. So future-wise, we would be really interested to do some qualitative coding on the online resources for their quality. That's also something that we're interested in moving towards, trying to build a classification model that could detect useful pages. But again, we're not quite there yet. And so just to close, so some of these future directions for all of these different categories of environments. Our contract with MedU is closely coming to a close. So we've shifted our attention in terms of working with content management systems, developing and evaluating SCORM compliant e-learning modules that are hosted in the Google Learning environment, which we use for teacher professional development purposes, and that's currently supported by a University of Utah Seed grant that's headed by Aaron Fisher, who works in the counseling program. We're interested in teaching them skills for managing difficult students in the classroom, but we're also interested in expanding the scope of these e-learning modules to using different types of technologies and training the users on the Adobe Creative Cloud suite of applications. We're also collaborating with Kirsten Butcher and the Natural History Museum of Utah to evaluate their research-based web platforms, which has really neat three-dimensional representations of like dinosaur bones, so that the students can learn about and classify which species of dinosaur those bones belong to. And in this case, we're interested in using the same M-Observer app that we use to model the tutorial discourse to see if we can perhaps build a tutorial script that hopefully could guide, that we could evaluate, and that would guide how to design a pedagogical agent that would support the students in acquiring some of these critical thinking skills. In terms of the open-ended learning, our work with the open-ended learning environments, so we're still pursuing our research with N-Browser by training and validating more predictive models of learner behaviors. We're especially interested in things like disengaged learning and them gaming the system, since mostly in your first iteration of the system, you have a lot of problematic behaviors that we could be interested in detecting and responding to, hopefully so that we can better tease out these effects in terms of looking at if the adaptive version is adding anything to the quality of their lessons. And we're also interested in expanding some of the crawling and clustering techniques that we use to additional STEM domains, so covering more subject areas than mathematics. And very importantly, validating some of the simulation parameters against actual human learner data. So some of the assumptions that we make for these simulations, we probably have to cross-check against actual human learners to make sure that those parameters are reasonable. And a good example is like the number of pages visited by the learners. Most learners for a network size of 100 won't navigate to all 100 pages. They'll maybe navigate to 10 or 20. And right now we're using randomly generated distributions of data because we don't know. But we have to go about actually validating that against actual human data that's a little bit more sensible to some of these limitations. And we also applied for an SF grant to look at evaluating a web-based visualization of these online networks that we refer to as N-Viewer. And we think that maybe making the online networks visible to the learners will be more conducive to better learning outcomes than the current version of N-Browser, which closes that, so that representation is visible for the learner. So with that being said, I'd like to thank Royce for setting up the talk, and also to acknowledge some of the funding agencies that supported our work. If you have any other questions or comments, maybe we can go through it over dinner, over lunch.
Let's give Eric a big hand.